A single mature supermassive black hole contains enough energy to power human civilization for 1 trillion years. That's a billion times longer than the current age of the universe. This isn't science fiction, it's pure physics. Some researchers have already begun exploring theoretical frameworks for extracting this energy, though their most alarming implications remain largely unpublished. By the end, you'll understand why some scientists believe that attempting to tap into these cosmic powerhouses could be humanity's greatest achievement or trigger a catastrophe beyond our comprehension. Black holes might not just be objects in space, they might be nature's ultimate warning sign. Let's start with what appears to be merely an engineering challenge: the mind-bending technical requirements of approaching a black hole's event horizon. Any vessel designed to harvest energy from a black hole would need to withstand forces that make our deepest ocean trenches seem like a gentle summer breeze. The closest stable orbit around a stellar mass black hole experiences gravitational forces millions of times stronger than Earth's gravity, with temperature gradients spanning from near absolute zero to millions of degrees within meters. The smallest structural weakness would cause catastrophic failure. But that's not all. The vessel would need to survive extreme radiation, time dilation effects, and magnetic fields powerful enough to tear apart atoms. What's particularly unsettling is that our most advanced computer simulations fail when modeling these extreme conditions. Engineers working on theoretical black hole harvesters have discovered that conventional physics breaks down in ways we don't fully understand. Some of their test simulations show impossible results. Materials that should disintegrate instead behave in ways not yet explained by current models of matter. But if you think the technical challenges are intimidating, wait until you discover what happens when we actually begin extracting energy from a black hole's rotation, a process that could accidentally create something far more dangerous than the black hole itself. The second challenge takes us into far more dangerous territory. Harvesting energy could accidentally accelerate a black hole's rotation to physics-breaking speeds. This is where the true cosmic horror begins. Imagine a spinning black hole, not just spinning, but whirling at near the speed of light. The space-time around it doesn't just curve, it gets dragged along like water in a cosmic blender, creating what physicists call the ergosphere. The Penrose Process, our best method for extracting black hole energy, works by dropping matter into this ergosphere at precisely calculated angles. When done correctly, the black hole's rotation transfers energy to this matter, which we can then collect. But here's where things get nightmarish. Each extraction increases the black hole's spin relative to its mass. Recent papers from Princeton and Moscow State University have identified a theoretical tipping point. Past a critical spin-to-mass ratio, space-time around the black hole could begin to fracture. Some theoretical physicists believe this might create a naked singularity, something Einstein's equations predict is mathematically possible, but that most physicists consider too dangerous to exist in our universe. Why? Because unlike black holes, whose event horizons mercifully hide their singularities from the universe, a naked singularity would expose a point of infinite density and infinitely curved space-time directly to our universe. These calculations are so disturbing that several prominent physicists have privately suggested implementing a global ban on black hole energy research. But this pales in comparison to the third consequence, a disaster that wouldn't just affect our solar system, but could ripple across thousands of light years. Did you know that black holes don't just consume, they communicate? When disturbed, they release gravitational waves that travel at light speed across the cosmos. Now imagine what happens when we start aggressively manipulating a black hole's fundamental properties. The gravitational waves generated by black hole energy extraction wouldn't be like the gentle ripples detected by LIGO from distant black hole mergers. Mathematical models from Caltech and the Max Planck Institute suggest they would be directional, concentrated, and potentially devastating. Some scientists argue these waves would dissipate harmlessly over interstellar distances. Others warn they could maintain enough coherence to disrupt planetary orbits, stellar formation, or even trigger early supernovae in unstable stars. What makes this particularly concerning is the unpredictability. Our current understanding of gravitational wave propagation through different cosmic mediums is still in its infancy. We simply cannot predict with certainty how these waves would interact with distant stellar phenomena. A 2023 paper published in Astrophysical Journal Letters suggested a truly terrifying possibility. Under certain conditions, these artificial gravitational waves could potentially resonate with and amplify natural gravitational waves, creating a cascading effect that grows stronger rather than weaker with distance. If you find the idea of unleashing unpredictable gravitational tsunamis across our galaxy disturbing, what comes next will make you question whether black holes are hiding something even more fundamental about the nature of our reality. The fourth consequence takes us deep into theoretical territory, the risk of creating micro-tears in space-time that could expand uncontrollably. This is where black hole physics intersects with quantum field theory in ways that challenge our most fundamental understanding of reality. At the quantum scale, space-time isn't smooth. It's a foaming, bubbling landscape of virtual particles popping in and out of existence. Black holes already strain this quantum fabric to its limits. Now imagine actively manipulating the ergosphere of a black hole, where space-time is already stretched to nearly breaking point. According to calculations from the Perimeter Institute, aggressive energy extraction could potentially tear this fabric, creating quantum instabilities that spread outward from the black hole. What would this mean in practical terms? Potentially regions of space where the laws of physics become unreliable or even fundamentally different. Imagine a sphere expanding outward from the black hole at the speed of light, a boundary beyond which electronics might fail. Light might move at different speeds, or atomic bonds might become unstable. If such a disturbance reached Earth, the consequences would range from civilization ending to extinction level, depending on the severity of the space-time disruption. As nightmarish as this sounds, there remains one final revelation about black hole energy extraction that prominent physicists have described as beyond catastrophic, a scenario so extreme that several papers on the topic have been deliberately withheld from public archives. The ultimate cosmic danger of harnessing black hole energy is so profound, it challenges our understanding of existence itself. Energy extraction could potentially trigger a false vacuum decay, destroying not just our solar system, our galaxy, or even our local group of galaxies, but restructuring the entire observable universe at the speed of light. Our current understanding of quantum field theory suggests we might be living in a false vacuum, a universe that appears stable but is actually in a higher energy state than its true ground state. Like water that can remain liquid below freezing point until disturbed, our universe might be in a metastable state. The extreme conditions created by aggressive black hole energy extraction, combining singularity-level gravitational fields with quantum-scale manipulations, could theoretically provide the nudge that initiates a phase transition to the true vacuum state. Imagine a bubble of altered reality expanding outward at the speed of light. Inside this bubble, the fundamental constants that allow atoms to form, stars to shine, and life to exist would have different values. The laws of physics as we know them would be rewritten.